What's up, Pre-Calc? Here we are, section 10.1, sequences and series. I couldn't be there today, so because you couldn't have the best math teacher in the world, the next best thing is to have a video from the best math teacher in the world. So here we go, section 10.1. Of course, as we go along, I advise take notes, and if you need to pause the video at any point in time. This is for you guys, for your benefit. I'm basically going to be doing the examples from the book, section 10.1, just hopefully giving a little bit more explanation to help you guys out. Okay, here we go. Sequences and series. Sequences, guys, are just lists of numbers. Okay, you can see some down here, just lists of numbers. That's all it is. Series, what we're going to talk about, the second part here is adding up those numbers that are in a list, just basically adding up a list of numbers. That's what a series is. Okay, keeping these things separate is important. By the way, this is a topic you'll hit when you go to calculus for sure. Taylor series, things like that are very important and are a big part of calc, second year calc. So you best pay attention. You best learn a few things and remember a few things. Okay, here we go. First example, find the next four terms of the sequence. All I've done here is I've written out a sequence for you. And I've given you the first four terms, and we've got to figure out the next four terms. So we just look for a pattern right here. And if you take a second and look at these numbers, you can figure out which one's going to come next. If you just take a second. Okay, so this one increased by 5, and that one increased by 5 as well. So we can kind of draw the pattern here. That was a +5, and that was a +5, and that was a +5. So we can only assume that the next is going to be another +5, and then after that we're going to +5. We need four terms, so 1, 2, +5 again, and +5 again, and we can see that our sequence is going to follow with, let's see, 17 + 5, 22, 27, 32, and 37. Okay, we see the pattern. We've generated the next four terms. Okay, now suppose, and we could keep going forever and ever, right? This sequence could go on infinitely, and it would get infinitely large. But what we care about is how do we generalize this? So we're going to write what's kind of like function notation, but for sequences. Okay, I'm going to add a few things here. This first term of the sequence, we call it a sub 1. Okay, the second term of the sequence is, guess what? A sub 2, a sub 3, and we've gone all the way out to a sub 8, and it could keep going, right? Now let's suppose I want to know not for the first, second, third, or eighth term, but I want to know for the nth term. What can I come up with a formula in this sequence that for the nth term, which is any term in the sequence, can I figure out what that term would be based on where it falls in the sequence, n? Okay, so it looks like we started at 2, and each time we increased. So for a sub 4, we were at the fourth term, and we added 3 5s to 2. For the eighth term, how many 5s did we add? 1, 2, 3, 4, 5, 6, 7. So it looks like I need to take the number of the term, the index of the term, n, and subtract 1, and that's how many 5s I add to the starting number, which was 2. Okay. So if this seemed tricky to you, how I came up with this, then don't worry too much about it. We'll get more practice with this in a second. But you can see that if I plug in any number, so let's plug in this one, a sub 7, right? So I take 7, that's my n. So if I put a 7 right here, 7 minus 1 is 6, right? 6 times 5 is 30, plus 2 is 32. That gives me a sub n, or a sub 7. Okay, so I came up with the formula that gives me any term in this sequence. If I know where the term falls in the sequence, I can figure out what the term is. Okay, this one's going to be a little trickier. Let's try this one. Here's A1, A2, A3, A4, and we want to come up with the next four terms. So take a second. Can you figure out what the pattern is here as we move along the sequence? Well, let's see. From 2 to 5, we have an increase of 3. From 5 to 10, we increase by 5. From 10 to 17, we increase by 7. Looks like we're increasing by 2 more each time. So maybe the next one we're going to increase by 9. and then the next we'd increase by 11. You notice that these purple numbers I've written here, those are just odd numbers, and we just keep going up with the next odd number. So 9, 11, next odd number is going to be plus 13, plus 15. Okay, so again, we have a growing sequence, so 17 plus 9, 26. So 26, and then plus 11, 37, plus 13, 40, 50, plus 15, 65. And that sequence could keep going on forever, okay? So I've gotten A5, A6, A7, and A8. Okay, so this is my sequence, the first 8 terms. And the rule for this sequence, turns out, this one I wouldn't expect you guys to see right away, maybe after staring at it for a while. But a sub n is actually n squared plus 1. This is actually a pretty famous sequence because you'll notice n squared. Notice that each of these numbers is 1 more than a square number, right? So 2, that's 1 more than 1. 1's a square number. 5 is 1 more than 4. 4 is a square number. 10 is 1 more than 9. 9's a square number. 16, 25, 36, 49, 64, all the square numbers plus 1. Okay, but there was also this other pattern that each number was the next odd number greater than the previous. So interesting little series here that we can generate 1 more than each square number just by adding the next largest odd number to each previous. But that would be the general rule here. Okay, so a sub 8, we could plug in 8 here. 8 squared is 64 plus 1, 65. So this is basically our formula for our sequence, and it is in explicit form. We call this explicit form. Okay, I'll write a little of that on this. This is called explicit form. We're going to learn a different form here in a second. Okay, here, part C is a sequence that is already given to us. We already have the formula for it, the explicit form for this third sequence here. Okay, and we just want to generate the first 4 terms. So let's see here. A sub 1, what's that going to be? Well, this tells me that a sub n is 2 times n times negative 1 to the n. So a sub 1, I just take 1 and I put it wherever n shows up over here. Okay, so let's color code this guy. 2 times 1 times negative 1 to the first power. So n is 1, right? So I just basically substitute 1 in for n in my formula. And if we simplify that, we get, let's see, 2 negative 1 to the first power. That's negative 1. That's going to give me negative 2. So there's the first term of my sequence. Okay, let's find a sub 2. That's going to be 2 times 2 times negative 1 to the second power. Okay, what's that going to give us? For negative 1 squared, that's a positive 1 times 4. So our next term is positive 4. Okay, a sub 3, we just keep going. Our job is to generate the first 4 terms of the sequence. So we're just computing right now. Computers are really good at this, by the way. Now we're plugging in 3. Oops, that should be a 3. Now what do we get? 2 times 3, that's 6. Negative 1 to the third, what's that? Negative 1 to the third power, that's a negative 1, right? Because we have an odd exponent, times 6, negative 6. So you'll notice, as this exponent increases by 1 each time, our answer is going to flip from negative to positive, right? Because an odd exponent on a negative 1 is going to give us a negative answer. An even exponent on a negative 1 is going to give us a positive answer. And so on with that pattern. Okay, we got one more. A sub 4 equals 2 times 4 this time times negative 1 to the 4th power. What's that going to be? Let's put a 4 there, 4 there. 2 times 4, 8. Negative 1 to the 4th, positive 1. So we get positive 8 here. Okay, so we've generated the first 4 terms of our sequence. It looks like this: negative 2, 4, negative 6, and 8. And it will keep going in that fashion. Now that we see the pattern, we could probably come up with okay, so the next one's obviously going to be a negative 10, and then positive 12, so on. You see the pattern. Okay, so we know how to take a string of numbers and write a general form, explicit form formula for it. And we also know how to take explicit form and generate the first few terms of the sequence and learn what the sequence is doing. Okay, so there's that first example. Okay, moving on. Example 2, recursive sequences. The sequences we just did were not recursive. but they could have been written in recursive form. How do we deal with what we call recursive sequences? Okay, recursive sequence is a sequence where you're given the first term, or sometimes you're given the first two terms, and then you're told what to do from there. So this is basically the beginning term, and this term tells us how do we get the next term, and then how do we get the next term, and then how do we get the next term. Okay, so let's look at this formula that we have here. It says a sub n, the nth term. We need to take the n minus 1th term. Okay, so if we think about this, a sub n is after a sub n minus 1, right? Because this is the previous term in the sequence. So for each term, we need to take the previous term, add 2n, and subtract 1. Okay, so we have a1 equals 1. What about a2? So a2, oops. We're going to generate the first few terms here. A2 equals, let's see, well, n is 2 right now. So 2 minus 1, that means I have to take the previous term, a sub 1, and I add 2n. N is 2, right? So I can put a 2 here, minus 1. So all I've done is I've gone into this formula and I've put a 2 everywhere I see an n. And you see right here, I did that in my head, the 2 minus 1 part. I turned that into a 1 already, okay? And then we simplify. What can I put in for a1? Oh yeah, that's this term, the term I was already given. A sub 1, that's 1. So this can simplify to become 1 plus 4 minus 1. That gives us 4. So there's our second term of the sequence. Started with 1, now we're at 4, okay? So let's suppose that I need to get the 5th term of this sequence, okay? That's my goal, is to get the 5th term. Well, by now, hopefully you realize that I can't just plug 5 in, because if I plug 5 in, then what's going to happen here? I'm going to get a 4, so I need to know a sub 4 in order to get a sub 5. But in order to get a sub 4, I would need a sub 3. And in order to get a sub 3, I would need a sub 2. You guys get the idea. You need the previous term to get this term. So each term requires the previous term and depends on the previous term. Okay, so in order to get a sub 3, let's just do this then. We got it. In order to get to a5, we need to do a2, a3, a4 to get a5. Okay, so a3 is going to be a sub 2 now. We take the previous term, which we figured out a second ago, right? Plus 2 times n. N is now 3, right? Minus 1. What does that give us? Well, a sub 2, that's 4. We already figured that one out. Plus 2 times 3, that's 6. Minus 1, 9. Got that one. Okay. Okay, what's going to be a sub 4? I hope the color coding is helping, because it's kind of a pain in the butt. Okay, equals a sub, let's see, what's going to go here? A sub 4. That's 4, so previous from 4 is a sub 3. So we take the previous term, add 2 times n, which is 4, minus 1 equals, let's say a sub 3, that's 9, plus 2 times 4, 8, minus 1. What's that going to be? 16. Okay, last one. A sub 5. Oops, that was supposed to be red. Darn. Okay, that's a 5. That's a red 5. A sub 4 plus 2 times the previous term, which is 16, minus 1 equals, well, a sub 4 we just figured out, that's 16, plus 2 16s. Let's see. Yeah, 2 16s. That's a 32. I messed something up, didn't I? A sub 5, a sub 4. Oh, yeah. N's not 16. Yikes. It's 2n. N is 5. There it is. +1 respect if you caught that. Leave it in the comments below if you caught that, okay? A sub 4. We got 16 plus 2 times 5. That's 10 minus 1. We get 25. There's a sub 5. We did it. That's our goal. Hey, do you guys see a pattern? 1, 4, 9, 16, 25. These are the, anybody know? the square numbers. Wow. Interesting how we could generate the square numbers with this recursive sequence. Math is full of tasty little treats like that. Okay. Like this video if you like that. Okay. Don't forget, smash like, please. Okay. So we got a sub 5. Hopefully you get the idea of how recursive sequences go. Big idea is each term depends on the previous term. It's recursive. It repeats itself. Okay, the pattern repeats, and you look at the previous term. This one is an extremely famous, probably the most famous sequence ever, I imagine. Okay, it's the most in the math world. There's a lot of attention on this sequence, and in other worlds too. It shows up all over the place in Mother Nature, in science, in statistics, in business. It's all over the place. Anyway, here we go. Notice we're given two terms this time. We're not just given the first term, we're given the first two terms. Why is that? Because in order to get a sub n, not only do we need the previous term, but we need the previous term 2 behind the current term. Okay, so we take the two previous terms, add them together, that gives us this term. You may have heard of or seen this sequence before. Okay, so 1 is the first term, 1 is the second term. What's the third term? I'm not going to color code this time, I'm getting lazy. A sub 3. Well, that's going to be a sub 2 plus a sub 1, the two previous terms. And what are those terms? 1 and 1. So that's 1 plus 1, which is 2. Nice. Okay, next term, a sub 4. What do we get here? Well, that's the two previous terms, a sub 3 plus a sub 2. What are the two previous terms? 2 and 1. 2 plus 1, that's 3. So far we have 1, 1, 2, 3. What do we got next? A sub 5, that's going to be a sub 4 plus a sub 3. 4 was a 3, a sub 3 was a 2, so 3 plus 2, that's a 5. Okay, so you start to see our pattern here. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, 13 plus 21 is 34, and so on and so forth. This is called the Fibonacci. I think that's how you spell it, maybe just one N, Fibonacci sequence. Okay, I'd love to spend more time talking about the Fibonacci sequence. Fortunately, there are a bazillion videos on YouTube that explain it and show it way more and cooler than I could. So I would advise that you check that out. We don't have time right now. Hey, come to Math Club. We talk about this kind of stuff in Math Club all the time. But anyway, there's the Fibonacci sequence defined recursively for you. All right, let's move on. Okay. Example 3, determine if a sequence converges or diverges. Okay, so converges means to come together. Okay, that's what a converges means in context outside of math, when things come together, right? Like you came together with your family on Thanksgiving and then you diverged the next day because you couldn't stand to be with them. So you went out Black Friday shopping. Okay, so converge, come together, diverge, spread apart. And sequences either do one or the other. There's no middle ground. Okay, so here is a basic, you could call this a linear sequence, I guess. You might look and notice, oh, that's linear. That's kind of like y equals mx plus b, possibly. Okay, so how do we tell if this thing converges or diverges? Well, let's take the first few terms of the sequence. Okay, so a sub 1, what would a sub 1 be? Well, it's going to be negative 3 times 1 plus 12. So a sub 1 is going to be, let's see, 9, right? A sub 2, if we put a 2 there, negative 6 plus 12, 6. A sub 3, negative 3 times 3, negative 9 plus 12, 3. A sub 4, negative 3 times 4, negative 12 plus 12, 0. Hey, I see a pattern. Looks like we're just decreasing by 3 for each term. So the next one's probably going to be negative 3 and then negative 6 and so on. Okay, we've got a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6, and we could keep going. Okay, so the question is, does this sequence converge or diverge? Okay, so this sequence diverges. And the reason I can tell is as we move along in the sequence, our terms are not approaching any particular value. Okay, if we look at this on a graph, we can actually graph sequences and it gives us a good idea of their behavior, a lot like how graphing functions gives us a good idea of their end behavior. Okay, so if this is our n axis and this is our a sub n axis, okay, then right here will be n is 1. So where n is 1, a sub 1 is 9. So we're up here at 9. Okay, so there's 9, boom. Okay, and a sub 2, sub 3, sub 4, sub 5, sub 6. So there's 2, 3, 4, 5, and 6. And a sub 2 is 6, so that's like, oh, I don't know. Let's see, right here maybe. A sub 3, that's 3, maybe right there. A sub 4 is 0, right there. A sub 5, that's a negative 3. A sub 6, that's a negative 6. So our sequence has this kind of downward trend. Okay, it's linear, and we're not surprised. We just said a second ago, oh, this looks like a line, right? Negative 3x plus b, and our b would be positive 12. So this looks like a line with that negative 3 slope and a y-intercept of 12 possibly, okay? But really all this sequence is, it is a linear function just with a restricted domain, okay? The input values, our x values, can only be integers, positive whole numbers, okay? Anyway, if we were dealing with this function, we would describe the end behavior like this. Limit as x goes to infinity of f of x. Remember doing this? Where does this go? As x goes to infinity, our y value goes down to negative infinity, okay? So this is if it was a function. It's not a function, it's a sequence, so we talk about it a little bit differently. This is kind of what we learned in, what was this, chapter 1? Okay, now we're looking at sequences, and we're deciding, okay, this thing is just going to keep going down to infinity. It's not going to approach any particular value, so we know that this thing diverges. Okay, why does it diverge? Since a sub n approaches infinity as n increases. This is says approaches. Okay, so this sequence diverges, and the best way to tell is just to get the first handful of terms, maybe 5 or 6, graph them, and sometimes you can tell just by looking, but just graph them, see, okay, where are they going? Are they going anywhere in particular? No, they're going down to negative infinity, so we say diverges. If it's going up to positive or to negative infinity, that's how we describe it, okay? Let's look at another one. I just showed you one that diverges, so if you guess that the next one is going to converge, you'd be correct. Spoiler alert. Okay, this next one is going to be a recursive sequence. What does that mean again? Oh yeah, that means you get the first term, and then you're told what to do with that term to get the next term. So a sub 1 is 36, and a sub n equals negative 1/2 times a sub n minus 1. Okay, so here we go. We're given our first term, and we are given our formula for how to get the next term. So what we should do now is get the first few terms just like what we did before. Okay, so a sub 1 we already have is 36. Okay, what's the next term going to be? Well, it looks like a sub 2, I need to take the previous term, a sub 1, and multiply it by negative 1/2. So to get a sub 2 here, let me just label that. Here's a sub 1, a sub 2. I need to take the previous term, a sub 1, and times it by negative 1/2. So what's negative 1/2 times 36? Negative 18, right? Yeah. And to get a sub 3, we do the same thing. We take the previous term, a sub 2 now, which is negative 18, times it by negative 1/2. Negative 1/2 of negative 18 is going to be positive 9. Okay. Okay. Is our sequence converging or diverging? Well, let's keep going and we'll find out. A sub 4 is negative 1/2 of the previous term, a sub 3. So what's negative 1/2 of 9? Negative 4.5. Okay. And let's keep going. We're going to cut that in half again and times it by negative 1/2. Negative times negative positive 2.25, I believe. Yep. That's a sub 5. And we could keep going. We're going to get negative 1.125, right? Okay, that's a sub 6. Let's go one more. A sub 7 down here. What's going to be negative 1/2 of that? Let's see, 0.5, negative 0. Let's see, 0.5. I don't know. It's small. 0.5 something. Okay, You guys can calculate it if you want to be more precise. We don't need to be at this point. And my calculator is currently being used to record this video. So I'm just going to call it 0.5 something. Okay, I know that's close to that anyway. All right, I'm at 0.56, 25, maybe something like that. Anyway, let's graph it. A sub n, and let's graph our x-axis, which is now our n-axis, and n goes 1, 2, 3, 4, 5, 6, 7. Okay, so in a sub 1, we're all the way up here at positive 36. A sub 2, we're down here at negative 18. A sub 3, we're up here at 9. A sub 4, we're at negative 4.5. Every time we jump half the distance to 0, and we flip to the opposite side. That's what's happening, right? And we go to positive 2.25, and we go negative 1.125, and positive 0.5625. You can see that if this trend continues, we're basically just going to be dancing up and down, up above and below the x-axis here, okay? So you'll notice that this graph is actually approaching a value. If we were to keep going and going and going, what would you expect a sub 100 to be? What would you expect that to be? Something very, very close to 0, right? Ooh, would it be positive or negative? Looks like all my even terms are negative, so it would probably be negative 0.0000, something very, very close to 0. So yes, this graph does converge. Okay, since, I should say converges, since a sub n approaches, I'll write it down here, approaches 0 as n increases. So that's a convergence sequence, okay? Well, let's do one more of those. Okay, last sequence, we'll see if it converges or diverges. So this is part C. A sub n, this is defined explicitly, not recursively. So we just have negative 1 to the n power times n over 4n plus 1, okay? So what should we do first to tell if it converges or diverges? We should calculate the first 4 or 5 terms of the sequence. Whoa, jump cut, what just happened? Oh, I paused the video and I took a second to just calculate the first 12 terms of the sequence. Okay, so if you would take the time to do it yourself, just try plugging in 1 for here and here, and then plug in 2 for that end and that end, and calculate. Yes, it's mundane. Yes, it's tedious, but it's kind of necessary to get an idea of what this sequence is doing. So as you look, you notice every other term switches from positive to negative as we go by, and that happened here because every time n increases, this will switch from odd to even or from even to odd, which will change ultimately the sign of this thing, right? Negative 1 to an even power is positive 1. Negative 1 to an odd power will be negative 1, and that will determine the sign of this whole thing. So you notice how it switches back and forth from positive to negative, and the rest takes care of the rest. Okay, so negative 0.2, 0.22, negative 2.31, 0.235. We look and we see, okay, what's this thing doing? Is it approaching a particular value? Well, if you ignore the negative, it would appear as though it is 0.2, 0.22, 0.231, 0.235. We keep going, we get closer and closer to something, 0.244, 0.244, 0.245. Okay, it appears as though it's getting closer and closer to maybe 0.25, which is 1/4. Maybe it's diverging to that, okay? But we look and we see that it's not really approaching that because it keeps flipping back and forth between a positive and a negative value, okay? So if we graphed this, what would that look like? Okay, here's a sub n, here's the n, or no, here's the n-axis, excuse me. This is the a sub n axis. And as we move on, as n increases to the next term of each sequence, a sub n is flipping back and forth from positive to negative. Let's say here's 0.25. Okay, so it starts at negative 0.2, so that's like down, here's, let's say this is negative 0.25 down here. So it starts at negative 0.2, so maybe that's like right here, and then positive 0.22, so maybe that's right here. So it flips back and forth, and it gets closer and closer to the negative 0.25. and positive 0.25. Okay, and so it's going to keep flipping back and forth and getting ever closer to that boundary of positive 1/4 and negative 1/4. Okay, so what was the question again? Oh yeah, does this sequence converge or diverge? Well, if you look at just the evens, it's converging to positive 1/4. If you look at just the odds, it's converging to negative 1/4. But if you look at the whole sequence, which is what we're doing, it doesn't converge at all. Okay, it's approaching two separate values. It's going to bounce forever and ever, and it's never going to quite converge on anything. So we do say that this diverges, since a sub n approaches both 1/4 and negative 1/4 as n increases. Okay, so in order to determine if it converges or diverges at this point, all we do is we generate some terms and we look at the pattern and we decide, is it approaching one value, or is it bouncing around, or maybe it's shooting off to infinity or down to negative infinity. The only time it converges is if it approaches one singular value, like it did in the previous example here, where we were bouncing, but we were approaching the same value from above and below. Okay, that's the difference between convergent and divergent series. Hope that makes sense. Okay, here we go. Sequence versus series. Are you having fun yet? I sure am. Here we go. A sequence we've already talked about a lot. That's all we've talked about so far is sequences. Okay, I can give you an example of a sequence. How about 1, 3, 5, 7, 9, etc. All the odd numbers. Hey, there's a sequence. It's just a list of numbers. Nothing terribly special about this so far. Okay, here's a series. Ready? 1, 3, 5, 7, 9, ... Except instead of a list of numbers, it's a sum of a list of numbers. Okay, that's all a series is. Series is almost synonymous with sum. Okay. A sequence is a list of numbers, a series is a sum of numbers, and these things get confused a lot because they're used in similar contexts. Especially when you get to calculus, you'll learn about series right after you learn about sequences, and it'll be easy to get things mixed up. So for now, let's try to keep a clear distinction here. Okay, a sequence is just a list of numbers, a series is a sum of those numbers. Okay, so they're closely related though. Okay, if I were to take these first four terms of this sequence, this series, and add those up, 1 + 3 + 5 + 7, that would give me 16. If I take these four and add them up, that gives me 16. And if I ignore the rest of the series, okay, this is called the fourth partial sum. Why is it called the fourth partial sum? Because, well, it's not the whole sum. The whole sum would be adding up all these infinitely many terms. It's only a partial sum. It's only part of the series. And it's the fourth partial sum because it uses the first four terms. The fifth partial sum would be 1 + 3 + 5 + 7 + 9, which would be 25. Okay? The first partial sum would just be this term added to nothing else. Okay? So the fourth partial sum, also called S4. Okay? We can talk about partial sums with sequences as well. So if I said, hey, find the fourth partial sum of this sequence, you would just add up the first four terms just like you would do with a series, and it would be 16. So we talk about partial sums with both sequences and series. Okay, but if we're adding up an infinite amount of terms in a sequence, that we call a series. Okay, only call that a series. Anyway, let's suppose that you are told to find the fourth partial sum of this sequence. Okay, so here's an example. Find the fourth partial sum of a sub n equals -2 to the n plus 3. Okay, well, what does that mean? Oh, well, the fourth partial sum, that means take the first four terms and sum them up. Okay, so of course we could go infinite terms, but this says the fourth partial sum, so we only need to take the first four terms and sum them up. So the fourth partial sum has this notation, S4. Okay, so that is going to be the first term plus the second term plus the third term plus the fourth term. I'll write that out, A1 plus A2 plus A3 plus A4. Okay, now let's figure out what are those values. Well, A1 is negative 2 to the 1 plus 3. What's negative 2 to the 1? That's going to be negative 2 plus 3. Let's see, negative 2 to the 1. Oh, let's color code this to the 1 plus 3. That's A1 plus A2, which is negative 2 to the 2 plus 3 plus A4, negative 2 to the 3 plus 3, and add A4, which is negative 2 to the 4 plus 3, showing all my work. Okay, now I can simplify. Negative 2 plus 3, that's a 1, plus negative 2 squared, that's positive 4, plus 3, that's 7. Negative 2 to the third, that's going to be negative times a negative times a negative is going to be negative 8 plus 3, that's negative 5. So add negative 5. Negative 2 to the fourth, that's 16. Positive 16 plus 3, that's 19. Okay. Do I keep going? No, I was only told to find the first 4 terms. So 1, 2, 3, 4, 1, 2, 3, 4. Add them up. What do we get? 8. Oh no, this makes 20. 27 minus 2, 22. Wait, is that right? 8 plus 19, 27. Yeah, 22. There it is. Fourth partial sum. Nice. So all that means is take the first 4 terms, add them up. It's called S4. Okay. Let's find the S3. Let's do another example. Part B. Find S3 for the sequence A sub n equals 4 over 10 to the n. Well, S3 just means add the first 3 terms, right? The third partial sum of this sequence. So all we need to do is find the first 3 terms. So S3, that's going to be A1 plus A2 plus A3. That equals, well, A1 is going to be 4 over 10 to the 1 plus A2, that's going to be 4 over 10 to the 2 plus A3, that's going to be 4 over 10 to the third. That's it. 10 to the 1, that's 4 tenths. 10 to the 2, that's 4 hundredths. 10 to the third, that's 4 thousandths. Okay. Now, normally I'm an advocate for leaving things in fraction form, but in this case, since we have powers of 10 as our denominators, decimals are super handy here. It makes it way easier to get our, add these things up. 4 tenths, that's 0.4. 4 hundredths, that's 0.04. 4 thousandths, that's 0.004. If we add those up, we get 0.444. There's our partial sum, S3. Okay. Whew. Moving on. Okay, almost done here, guys. I want to pick your brain for a second here. Is there a way that we can add up an infinite amount of positive numbers and get a finite answer? Big brain question. Can we add up an infinite amount of positive numbers and get a finite answer? And one of the wonderful phenomena of mathematics is the answer, yes, we can. Okay, a convergent sequence or a series is what that is. Okay, so first let's just talk about a regular old, how about this series right here, 1 plus 4 plus 7 plus 10, etc. Okay, what would S1 be? What does this mean again? Oh yeah, this is the first partial sum. This is the sum of the first term with nothing else, so that would be 1. Okay, what about the sum of the first 2 terms? 1 plus 4, that would be 5. And what about the sum of the first 3 terms? 1 plus 4 plus 7, 12. And the sum of the first 4 terms, 22. And if we keep going, what's the next term in this sequence? 13, well, it looks like I'm increasing by 3 each time. 13, 16, 19. As I keep going, this sequence is just going to get larger and larger and larger. Okay, this sequence, I know it's a set of partial sums, but we can treat it like a sequence of numbers, just like the sequences before. if we were to graph this, this thing converges, or sorry, diverges, right? It goes off to positive infinity. If I keep adding bigger and bigger positive numbers to this sequence, our total term is going to get larger and larger as we go on. That goes off to infinity. This is an infinite sum, okay? Not very interesting. It's kind of obvious what's happening here, okay? But if we take a sequence like this, okay, this is where things start to get kind of bizarre, but also kind of intuitive here. This is a lot like the last one that we had. Okay, we got a tenth plus a hundredth plus a thousandth plus a 10,000th. Okay, this is a sequence of numbers that is totally legit. And if we turn it in from a sequence and we turn it into a series and start adding these terms, could I add these terms all the way out to infinity? I could. And if I did, what would I get? Does this does it keep getting larger and larger and go off to infinity like the previous one? Okay, or does something else happen? Well, it's kind of like the previous example where we had 0.4 plus 0.04 plus 0.004, except this one keeps going on forever. Okay, so let's look at the first few partial sums. Remember, the partial sum is just the sum of the first few terms. Let's see what happens here. Well, S1 is just the sum of the first term with nothing, so 0.1. And this S2, that's the second partial sum. That's 0.1 plus 0.01. That's going to be, let's see, what if we add these two terms? What do we get? 0.11. S3, that plus that plus that, 0.111. S4, all first four terms added up, 0.1111. You see the pattern here. What is the final sum going to be? Suppose we could get S infinity. What would that be? This is not correct notation, but we can get a sum here because we see the pattern. We see we're going to get 0.1 repeating, right? Never going to end. And it turns out that any single digit repeating after a decimal can be written as that digit over 9. Okay, if you don't believe me, check it on your calculator. 1 divided by 9, you're going to get 0.1 repeating. Works for anything. 2 divided by 9, that's 0.2 repeating. 3 divided by 9, that's 0.3 repeating. Oh yeah, because we know the 3/9, that's just 1/3. That's 0.3 repeating. All the same stuff. Okay, so this series, even though it's an infinite amount of numbers all adding up, it lands right here on a finite number, and a pretty small one at that. Okay, we'll talk more later about some very peculiar series like this that add up to some very familiar numbers that you might find somewhat bizarre and hopefully entertaining. Okay, but hopefully that just sets the stage for now. Okay, guys, last topic, almost there. Have I put you to sleep yet? Hope not. Wake up your neighbor if they're asleep. Here we go. Sigma notation. You guys have seen this before. I think, yeah, I remember helping some of you with this when you needed help in Algebra 2. So I do know that you have seen this before. This is Greek letter, capital letter sigma. Okay, this is a way, it's just a shortcut for writing out series or sums. Okay, and it always looks something like this. You've got some sort of a sequence term in here, or a explicit form of a sequence here, a sub n, and you've got a index and a starting point and an ending point. Okay, so let's add a few notes here. N is the index. That's just basically the label for each term. Okay, and the index increases by 1 each time, each term. You'll never see the index jump up by more than 1. It'll always go up 1 each time. Okay, where does the index start? Whatever it is here. In this case, it's starting at 1. So starting value of index. Okay, so in this case, the first value of the index is 1, so the first term is going to be a sub 1. And we're going to add up every succeeding term until we get to k. So k is the ending value of index. Okay, so this series can be written as a sub 1, since n starts at 1, plus, well, what's next? Well, remember, the index increases by 1 each term. So the next term is a sub 2, and the next term would be a sub 3, all the way out to, guess what? A sub k. K is the end value of our index, okay? Ooh, big brain question. What value goes right before a sub k? That's right, a sub k minus 1. 1 less than k, right? Because it increases each time, okay? So this is just general, how does sigma notation work? So let's do a couple of examples. What are you going to be asked to do in your homework? Because that's why we're all here, right? Here we go. Let's do a quick example. What if we had sigma n going from 1 to 5 of 4n minus 3? Can we calculate this sum? Okay, remember sigma just means sum. So we're basically adding up a bunch of terms. How many terms? Well, n is going to go from 1 to 5, so 5 terms. Okay, and here is our explicit form for our sequence inside this series here. So what's our first term going to be? Well, our first term is n equals 1. So we've got 4 times 1 minus 3. That's our first term, a sub 1, plus, what's next? Oh yeah, our index increases by 1 each time. So 4 times 2 minus 3, right? There's n that increases by 1 each time. So 1 increased plus 4 times 3 minus 3 plus 4 times 4 minus 3. If you're paying attention, you know when I'm going to stop. I'm not going to go on forever. Plus 4 times 5 minus 3. When do I stop? Plus, you're right, I stop here. Why? Because that's up here. The 5 is my k, tells me when to stop. So my n made it to 5, I stop. Don't add anything else. Now we just simplify and add, and we have calculated the sum. Okay, this is just us getting used to this notation, how it works. So what's this going to be? That's going to be 1 plus 5 plus 9 plus 13 plus 17. Yep, we just add all those things up. Did I make a mistake somewhere? Nope, I don't think I did. 1 plus 9, that's 10, plus 30, that's 45. 45 is my sum. Okay, let's do a couple more. If you feel like you got the hang of this and you want to get started on the homework, go ahead. But I feel like we should probably do just a couple more just to make sure we know exactly what's going on here and to complete the notes. Example 2. Sigma notation 7, n equals 3. And 6n minus 3 all over 2. Let's try this one. Oops, sorry, couldn't see that. Now you can. Dang, come on, troll. Get it together. Okay. Well, where does n start? N starts at 3, and it increases by 1 until we get to 7, and we add all those terms up. Okay, so let's get this done. 6 times n is 3. The first one is 3. There's my first term. How many terms am I going to have? 3, 4, 5, 6, 7. 5 terms. Right? So I got that one. That's where n equals 3. What happens next? N equals 4. What happens next? N equals 5. What happens next? N equals 6. What happens next? N equals 7. What happens next? Nothing, because 7 was my ending point. So n increased by 1 each time till I got to 7. Once I'm at 7, I stop because this told me to stop. Now we just add it all up. What do we get? We get 18 minus 3 is 15 divided by 2. 15 halves plus 6 times 4, 24, 21 over 2. 21 halves plus 30, 27 over 2 plus 6 times 6, 36, 33 over 2. This is a bummer. 6 times 7, 42, 39 over 2. Okay, hey, look, we got common denominators. We can just go ahead and add that. 15 plus 21 plus 27. Let's see here. I did grab my calculator, so I can get this done accurately and quickly for you guys. 135 over 2. Does that simplify? Nope. There it is. That's our sum. Are you guys ready for the last one? I certainly am. Let's do this. Example 3. Last one. You're almost there. You can feel it. Ooh, but this one's interesting. N equals 1 to infinity. What? Of 7 over 10 to the n power. Infinity. How the heck are we going to add up infinite terms? Well, I think once we add up the first few terms, you'll see exactly what's going on here. Okay. What's the first term we'll be adding? Well, n is 1, so our first term is going to be 7/10. Right? 10 to the first power, just 10, plus 7 over 10 to the second power, n is 2. Then n is 3, and then n is 4. How many of these would I have to write? Infinite of them, but no one's got time for that, so we'll just do a dot, dot, dot. Okay? 7/10. What should we do now? Maybe let's apply these exponents. That's 7/10 plus 7/100 plus 7/1000 plus 7/10,000. Okay, plus dot, dot, dot. What is this? Oh yeah, this is 0.7 plus 0.07 plus 0.007 plus 0.0007. Look familiar? Okay, what is this? This is, when I add all this up, what am I going to get? 0.7777777 repeating, right? Going on forever. What is that again as a fraction? Remember that trick I showed you? 7/9. Okay. If you don't believe me, divide this on your calculator. It's going to give you 0.7 repeating, which turns out to be the sum of this infinite series. Okay, it is a convergent series. It goes, the index goes out to infinity, but the sum approaches 7/9. Okay, so you should be able to recognize that as you move forward. Okay, well, I hope you liked that video, and I hope you learned from it, and I hope it helps. And I hope you do well on the homework. Guys, help each other out. Make this experience not as horrible as it has to be. And I'll see y'all on Monday, hopefully with a bunch of graded tests for your enjoyment. Hey, have a good weekend. Bye.